Hello everyone and welcome back to another tutorial video. This week we're going to be taking a break from our common tutorial structure to back up and rediscuss a number of topics that are central to the material covered in Stat 231, but which are difficult and cause a great deal of confusion. In today's video, I'm going to spend the bulk of the time discussing the differences between random variables and their realizations, estimators and estimates, sampling distributions, and the underlying distribution, as well as re-emphasizing the relationship between the target population, the study population, the sample, and how the various types of errors we have discussed come into play. I'll also be re-emphasizing the central limit theorem and what approximations are and are not appropriate. There's a couple of points to make on this. First, none of this material is new. Some of it's from Stat 230, some of it's from earlier in this term, but this should not be the first time you've seen it. Second, this material underlies much of the confusion from Quiz 5, and I've received plenty of questions, thank you for that by the way, please always reach out when you need, regarding this material specifically. I'd advise you then to watch through this tutorial even if you feel as though you understand the material. It's my goal to piece together these concepts so that you can see how they all fit together. Now, with that, let's get started. Perhaps the core concept in probability and statistics is that of the random variable. The concepts of random variables were first covered in Stat 230, where you learned that a random variable is a function that assigns a real number to each point in a sample space. In simple terms, random variables are quantities that can take on numeric values, where the values that they take on are due to a random process. We may think of counting the number of heads in a series of coin flips as a random variable. If we have a jar of candies and we pick one out, we may define a random variable based on what type of candy is observed, where the numbers we pick for any given type are arbitrary. In a population, we may think of the height of a randomly selected individual as a random variable, where here the randomness comes in due to the selection process. Now, statistics in particular is at its core a subject where we are observing random processes and then trying to make sense of what we observe. Consider, for instance, the random variable that counts the number of heads in 10 flips of a coin. We'll call this x. In a probability course, we may be interested in the abstract notion of what is the probability that x is equal to 4? Here we make some assumptions about the coin, for instance, that it is fair, and then we can compute this probability using an underlying distribution. Note that the random variables at all points in this process remains abstract. By this I mean that there never actually is a coin, and we never actually make observations of this random variable. We simply address possible realizations that this random variable could take on. In statistics, we flip this around. Instead of letting x represent some abstract coin, we start with a coin in the real world. We're interested in knowing what is the probability that this coin comes up heads, and we wish to use statistics to answer that question. For this, we have to perform an empirical study. For the coin flipping example, this empirical study is likely to be an experiment where we repeatedly flip the coin. Now, remember that x was defined to be the random variable that is given by the number of heads on 10 flips of a coin. Let's say that I actually flip a coin 10 times. Now, I can compute the value of x that we actually observed in our experiment. This is going to be some integer number between 0 and 10, and it's going to follow a binomial distribution with an unknown probability. If we knew the probability, then what good would this experiment be anyways? Once we have observed a value, we denote this realization by a lowercase x. Reading the Stat 230 course notes, quote, we generally denote random variables in the abstract by capital letters, x, y, etc., and denote the actual numbers taken by the random variables by small letters, x, y, etc. So let's recap. Capital X is a random variable which counts the hypothetical number of heads in 10 flips of a coin. Lowercase x is the observation of this random variable in a particular experiment that we ran. Capital X therefore has a distribution, it's random, and we can make informative probability statements about it if we are willing to make assumptions regarding the parameters. Lowercase x, on the other hand, is just some number. It's fixed, non-random, and if we actually run the experiment, we know exactly what it equals. Now, it's important to realize that lowercase x was not the only possibility before we ran the experiment. Capital X could have taken on other values. That's what we mean when we say that it is random. Lowercase x, on the other hand, is always fixed. It corresponds to one specific experimental realization. The differences between random variables and their realizations were, as noted by the quotes above, concepts carried forward from Stat 230. However, they're fundamental to Stat 231, and so I want to spend another minute going over some examples. In each of the following scenarios, I'm going to pose a question of interest in statistics. Just like, what's the probability that this coin turns up heads? For each of these possibilities, I want you to think of a random variable that will be useful in answering this question and map this onto a realization of that random variable. While doing so, it's helpful to actually write this down with the correct notation. Remember, capital letters are random quantities that are abstract notions of what might happen. Lowercase letters represent actual observations that we have made. You ready? Question 1. How tall are people on average? For this question, there is one choice of random variable that seems to work better than others, which is taking capital X to be the height, say in centimeters, of an individual. In this case, we are viewing X as mapping from the elements of the sample space, which here is made up of people, to real numbers representing heights. If we selected one individual at random, perhaps we observe a height of 170 centimeters. This would be lowercase x in our sample. Of course, in order to actually select an individual, we would need to define a scheme for drawing samples, but we'll touch on this later. Question 2. What proportion of songs are over 5 minutes in length? Here, the random variable is perhaps less obvious. It might seem like we should use length of song as a random variable. However, this does not give us the easiest path to what we are interested in. Instead, what if we defined a random variable y, which takes a value of 1 if the song's over 5 minutes, and it takes a value of 0 otherwise? Doing this, we can see a similarity between this question and our coin flipping example. Taking inspiration from there, you could have also defined y to be, for instance, the number of songs in a 10-song sample, which are longer than 5 minutes. This will work in the same way. In any event, here lowercase y would be observed when we select a song at random, or perhaps 10 songs at random, and look at whether it is longer or shorter than 5 minutes. Question 3. How many customers arrive at a store every hour? We again have some choice in the underlying random variable here. We could, for instance, take z to be a random variable that counts the number of customers that a store has arriving over the course of 1 hour. Then, if for some particular hour we sat at the doorway to the store, we could count up the number of people who entered, which would give us our observed lowercase z. There are other options, of course, but let's go with this one. So to recap, a random variable is a quantity which takes on real values according to some probability distribution, a distribution that may or may not be known, and which is an abstracted view of a population or process. We denote random variables by capital letters. When we actually begin to observe the population or process through some sort of empirical study, we can begin to talk about realizations of the random variable. Realizations of the random variable are denoted with lowercase letters and are just some numbers. They're no longer random and they do not have a meaningful distribution. I stress these concepts repeatedly, not just for their own importance, but because the same distinction shows up over and over again. To this end, let's discuss estimates and estimators. Consider the definition of a point estimator in the course notes. Quote, an estimator, theta tilde, is a random variable which is a function of g of the random variables y1, y2, up to yn. There's a few important things to clarify in this definition. First, as is stated directly in the definition, theta tilde is a random variable. We know that this has to be the case since it's a function of other random variables. This brings us to the second point. An estimator is some function applied to a set of random variables which were denoted in the definition by capital Y1 through capital Yn. The easiest way to conceptualize what it is that we are talking about here is by considering an empirical study. In an empirical study, be it an experiment, survey, or observational study, we make n observations from the study population or process, which forms our sample. Before the study has been performed, we can think of our sample as a collection of n random variables denoted y1 through yn. If an experiment involves flipping a coin 10 times in a row, then we may define y1 through yn to be random variables that take on a value of 1 if a head is observed and 0 otherwise. Before the experiment has been run, these quantities are random variables. Now, once the sample has actually been observed, we have the corresponding lowercase y values, lowercase y1 through lowercase yn, which are just numbers. These are our actual observations. Back to the conception of an estimator then, you can think of an estimator as a function of the random variables from a hypothetical sample. Some common examples would include the mean, the variance estimator, or even an order statistic, like the maximum. Note that we must be careful to keep our notation consistent. Theta tilde is a function of capital Y1 through Yn and is a random variable. What happens when we take our actually observed values in our sample, lowercase y1 through yn, and plug those into the function? This produces an estimate. Quote, "A point estimate of a parameter is the value of a function of the observed data, lowercase y1 through yn, and other known quantities such as the sample size n. We use theta hat to denote the estimate of the parameter theta." So when we take our observed data and we plug that into an estimator, we get an estimate. An estimate is just a number, which is based on the values that we happen to observe. We emphasize this by writing the function of lowercase letters rather than uppercase letters. So for instance, the sample mean is an estimate which corresponds to the mean estimator. Estimates are just numbers. They are simply values. So we have the concept of theta tilde, which is a random variable that we call an estimator. Because it is a random variable, it has some distribution associated with it. We conceive of an estimator as being a function of random variables that we could hypothetically sample. When we actually take a sample and make observations for those hypothetical random variables, we can plug those values into the corresponding function and generate an estimate, which we denote theta hat. An estimate is a fixed number and does not have a distribution. We can think of our estimate as a realization from the estimator random variable, just as we thought of lowercase x as a realization of the random variable capital X. We can think of theta hat as a realization of the random variable theta tilde. Now, sometimes we will use notation that is more specific to the problem at hand than theta tilde or theta hat. In fact, throughout this course, we have seen this plenty of times already. For instance, we have used lowercase y bar to denote the sample mean, which is an estimate. Let's think back to the 3 questions asked when dealing with random variables to reinforce this point. Question 1 dealt with a random variable, x, representing the height of an individual. Instead of taking one individual, let's say that we observe n individuals. As a result, we now have a sequence of n possible random variables, x1 through xn, which represent the heights of randomly sampled individuals in the population. We are concerned with the mean of these individuals, and so an intuitive choice for an estimator is the mean of the observations. That is 1 over n times the sum of the random variables. We could call this theta tilde of x1 through xn. However, we tend to reserve special notation for the mean estimator, capital X bar. In order to form our estimate of the mean, we could take a sample lowercase x1 through lowercase xn, and using these values compute the sample mean, a process you are all familiar with. Then, the value capital X bar is a random quantity with some distribution, and the sample mean is a number with some specific value. Question 2 dealt with a random variable y, which served as a binary indicator of whether a song exceeded 5 minutes in length. Again, instead of viewing this referencing a single song, we can consider a hypothetical sample of songs, where each of the n songs we assign a random variable, capital Y1 through Yn. Each of these random variables will take a value of 1 if the sampled song is longer than 5 minutes and 0 otherwise. Just as in the first question, we can conceive of an estimator theta tilde as capital Y bar and use the sample mean to estimate the proportion of interest. In the case of binomial random variables, sometimes we use a slightly different notation. Instead of viewing the sample as n realizations from a binomial 1 theta distribution, we could view the whole sample as a realization from a binomial n theta distribution. Remember that when you take the summation of binomial random variables, you get binomial random variable back. Here, we typically denote the random variable y to be the number of successes. For a music example, that is the number of songs that are longer than 5 minutes. And we use the estimator capital Y over n. Then our estimate is the observed lowercase y over n. This is mathematically equivalent, and whichever you prefer to use will suffice. Question 3 took a random variable z to represent the number of customers arriving to a store in an hour. The process should be feeling familiar now. We define a sample of random variables, capital Z1 through Zn, to be the hypothetical observations for the number of customers arriving across many hours. We take theta tilde to be an estimator where, again, the mean makes sense, so we may assign it the special notation of capital Z bar. We can then use the sample mean, lowercase z bar, as an estimate for the value of interest. What if we had been interested in the median number of customers arriving per hour instead? The experiment and random variable outlined should still suffice. However, we would want to select a different estimator. Perhaps now we take theta tilde to be given by the empirical median. Again, theta tilde would be a function of the random quantities, and so it is itself random. Once we have a sample, we can compute the sample median as a particular estimate. Now, as has been emphasized throughout this discussion of estimators and estimates, estimators are random variables, and random variables have a distribution. As a result, every estimator has a distribution, and we give this a special name, the sampling distribution. The sampling distribution of an estimator, simply, is the statistical distribution associated with that estimator. So we have an estimator of interest, theta tilde, which is a function of n random variables, denoted capital Y1 through Yn. Questions of sampling distributions revolve around questions of the distribution of these estimators. Sometimes we can determine the sampling distribution explicitly. If, for instance, we know that capital Y1 through Yn are Gaussian random variables, and we're using the mean estimator, we know that the means of Gaussian follow a Gaussian distribution as well. As a result, we can conclude that when the underlying random variables are Gaussian, the mean estimator has a Gaussian sampling distribution. There are two important points to make on this. First, we must be careful to differentiate the underlying distribution of the random variables, that is, the distribution of capital Y1, Y2, and so on, from the sampling distribution. These quantities will not, in general, be the same. Sampling distribution is going to depend on the underlying distribution, but it will also depend on the functions that's being computed, as well as on the sample size. When you're told that the underlying random variables follow some distribution, it's important to not conclude that the sampling distribution is the same. Second, while in this above example we stated that the distribution remains Gaussian, we have not yet concluded what the parameters of the Gaussian distribution will be. This is where your knowledge from Stat 230 will be important again. I'm not going to walk through the complete derivation of the expected value or standard deviation of our mean estimator, as this is done in the course notes and relies mostly on material from Stat 230. However, I will remind you of a few properties. Consider two random variables, x1 and x2, which are independent and identically distributed. First, we know that the expectation is linear. What this means is that the expected value of a times x1 plus b times x2 is given by a times the expected value of x1 plus b times the expected value of x2. This lets us pull constants out front of expectations and separate them over addition. When we have a constant multiple in a variance expression, that comes out front squared. So variance of a times x1 is equal to a squared times the variance of x1. Third, if we have two independent quantities, then the variance of a summation is the sum of the variance terms. That is, the variance of x1 plus x2 is equal to the variance of x1 plus the variance of x2. Combining these second and third results gives us the fact that the variance of a times x1 plus b times x2 is equal to a squared times the variance of x1 plus b squared times the variance of x2. As a final result, remember that if c is some real valued constant, then the expected value of c is simply c, and the variance of c is 0. Taking these results together, you should be able to derive the fact that for a mean estimator, we have the expected value of capital X bar is equal to the expected value of x, the variance of capital X bar is the variance of x divided by n, and the standard deviation of capital X bar is the standard deviation of x divided by the square root of n. Please, please, please take the time to work this out on your own. This is not going to be true of every estimator, but the process by which this is found out is vital for success in this course. It's also important to recognize this process does not depend on the underlying distribution of x. The mean estimator will always have these traits. With that, we could return to our example of the Gaussian mean and determine that the sampling distribution is a Gaussian with mean expected value of y and a standard deviation given by the standard deviation of y divided by the square root of n. Note that here, as was previously mentioned, the sampling distribution depends on the underlying distribution, the estimator that we are using, and on the sample size. Now, there are at least two questions remaining. First, what happens when we consider the estimates rather than the estimators? And second, what if we're not using Gaussian random variables? I want you to think about the first question for a moment. If you are asked questions regarding the distribution of our estimate, say little x bar, how would you approach these? I'd advise that you pause this video now and give this some thought. Otherwise, I'll start to fill in these details. Remember, we stressed that an estimator is a random variable and has a distribution, where an estimate is just some number. We can then think of estimates as constant values. They are not random at all, and as a result, there are no meaningful distributions to talk about. In terms of Stat 231, every number has a couple of key properties. First, the expectation of a number is just that number, and second, the variance of a number is 0. Moreover, every probability statement with a number will either take a value of 1 if the statement is true, or 0 if the statement is false. If we know that, for instance, little x bar is given by 4, and we are asked what is the probability that x bar falls in the interval from 5 to 10, we know that it does not, since 4 is not between 5 and 10. As a result, the probability is 0. If, on the other hand, we are asked what is the probability that little x bar equals 4, this is true, and so the probability is 1. Always remember, estimates are just numbers. If you're ever in doubt, replace the lowercase symbols with their corresponding numbers, and then try to work out what makes sense in that way. The second question, what if we're not using Gaussian random variables, prompts another important discussion. In this course, there will be times where you can compute the exact sampling distribution of a particular estimator, given the underlying distribution and results that you know. Whenever the exact distribution is available, it should be used. However, there are many other estimators you may experience which we do not have a closed form sampling distribution for, based on the content of this course. What then? Well, that's where the handy-dandy central limit theorem comes in. This is again a concept that was talked about throughout Stat 230 and is assumed knowledge coming into this course. I would suggest that you review Chapter 10 of Stat 230 course notes for complete details. However, roughly speaking, the CLT allows us to conclude that, for large n, the estimator of the sample mean will be approximately normally distributed with a mean of expected value of x bar and a standard deviation given by the standard deviation of x bar, the two terms we just computed. We can therefore use the central limit theorem to approximate the sampling distribution of estimators that are based on the mean of random variables in our sample. Of course, in order to use this in practice, you will need to feel comfortable computing Gaussian probabilities. But this is once more a skill that is a must-have for Stat 231, not just for CLT calculations, but for many of the concepts we address. It's something you should certainly practice if you do not feel comfortable with it. So, heading back to the 3 example problems we have been considering, let's consider how we might approach the sampling distributions. The first problem, where we're concerned with the mean height of the overall population, is a case where the underlying distribution is probably not clear. Oftentimes, with quantities like height, we're going to assume it's normally distributed, which would allow us to conclude that the mean has an exactly Gaussian sampling distribution. Even if the underlying distribution is non-normal, so long as we take n to be fairly large, we would expect that the CLT will apply and we can use a Gaussian distribution for sampling. In the second case, where we are considering the proportion of songs which are greater than 5 minutes long, we have a couple of options. Taking the notation where capital Y represents the summation of capital Y1 through Yn, we know that Y has binomial n theta distribution. As a result, we can make probability statements about Y over n, which is theta tilde, by converting this expression to probability statements regarding Y. If we wanted to know the probability that theta tilde was less than 0.5, for instance, this is the same thing as asking what is the probability that Y is less than 0.5 times n. We can then use the exact sampling distribution of Y to compute the necessary probabilities. Alternatively, we can view the estimate theta tilde as a mean and apply the CLT again. If we have a large enough sample, this normal approximation to the binomial becomes sufficiently good, and the two results will converge. In this course, you should always try for the exact probabilities unless they are not available or you are specifically told otherwise. Finally, in the case of the number of shoppers arriving per hour, we likely have no choice but to apply the central limit theorem. So long as our sample size is moderately large, we can use a Gaussian as the approximate sampling distribution here and work with the CLT. To recap what we have discussed so far, random variables, which we denote with capital letters, are abstract quantities which have some distribution. When we make explicit realizations of these random variables, we denote the observations with lowercase letters and treat those as numbers. An estimator is a function of random variables, which makes it a random variable itself that seeks to compute some quantity of interest in our population. When we realize a sample, we can plug those observations into our function to produce an estimate, which is just some number. Estimates are viewed as realizations of our estimators. Since estimators are random variables, they have distributions. We refer to these as sampling distributions. The sampling distribution of an estimator generally depends on the underlying distribution of the random variables, on the function that the estimator is comprised of, and on the sample size. Often, we are not able to compute sampling distributions directly and instead must rely on the central limit theorem to approximate them. When doing so, it's important to be able to compute the mean and the standard deviation of an estimator using the techniques that were covered in Stat 230. Finally, we recall that estimates, being numbers and not random variables, do not have any meaningful distribution. These concepts cause the bulk of the confusion on quiz number 5, and I would advise that you consider these definitions deeply and play around with the concepts. They are not easy, certainly, but they are incredibly important. When looking at a problem, you should be able to identify what is random, what is constant, and use this information to discuss the distributions of the random quantities and the values of the constants. Now, I also promised that I would briefly review the concepts of target populations, study populations, and samples, including the errors within them. This will be very brief, and I would recommend you checking out the tutorial on PPDAC for more information. A target population or process corresponds to the set of all individuals that we wish we could study. In general, we're going to be interested in some attribute of the target population, which we will hope to estimate. We can call this theta 1. Thinking back to our examples, theta 1 would represent the average height of a person across the entire population for question 1. It would represent the proportion of all songs that are longer than 5 minutes for question 2. And for question 3, theta 1 would give the average number of customers at the store in any hour. The study population corresponds to the set of all individuals that we actually have access to in order to study. Normally, the study population will be a subset of the target population, but this will not always be the case. Study population is defined by the study protocol that is outlined. For instance, in question 1, maybe we randomly sample students at the University of Waterloo to estimate the average height of all individuals. Here, our study population becomes University of Waterloo students enrolled in March 2021. In question 2, maybe you rewrite some code to randomly select songs from Spotify. Here, our study population becomes all songs that are available through the Spotify API in March of 2021. What about for question 3? How might we define a study population here? I'll leave this for you to decide, and feel free to email me with questions that you might have. The attribute of interest will exist as well. Here, we refer to it as theta 2, so instead of representing the average height of all people in the world, theta 2 would represent the average height of all students at the University of Waterloo in March 2021. Similarly, instead of being the proportion of all songs that are longer than 5 minutes, in our second example, theta 2 would represent the proportion of available songs on Spotify that are over 5 minutes. Once we have a study population, we can actually do our sampling procedure. Our sample is formed by selecting units from the study population to be included in our actual analysis. Once we have these observations, we can begin to actually estimate the parameters of interest. Based on the notation we have been using throughout, this would mean that we can produce theta hat values computed directly from our observations, which denote the estimates of the parameter in the sample we selected. For instance, theta hat may represent the sample mean of heights for students that were selected, or it may represent the observed proportion of songs that were over 5 minutes in length. We have our target population with its attribute theta 1 that we want to know about. we generally do not have access to the target population and instead define a study population which may or may not be a subset of the target population that we do have access to. Study population has a corresponding attribute denoted theta2, which corresponds to theta1 from the target population. Finally, our study population we take a sample of, and in this sample we compute an estimate of the parameter, which we denote theta hat. Ultimately, we hope that theta hat is a good estimate for theta1. However, there are biases and errors that may be present. First, we have study error. Study error occurs when the study population is not reflective of the target population. By way of our notation, if study error is present, we are saying that theta1 is not equal to theta2. For instance, consider the third example that we have been neglecting this whole time. Theta1 represents the average numbers of customers shopping at a store in an hour. If we designed a study to be run in March of 2021 with the hopes of estimating this value, our study population will necessarily consist of hours that the store is open in March of 2021. Can you think of anything going on that might make it so that the average during March of 2021 given by theta2 is different than the overall average given by theta1? Even when we do not have any study error, perhaps you're willing to assume that the average height of students at Waterloo is essentially the same as the average height of people around the world. Though there are some concerns here. For instance, how many 4-year-olds do you know who are enrolled at Waterloo? There are further sources of error that you still might observe, in particular, sample error and measurement error. Sample error generally refers to the case when the sample is not reflective of the study population more generally. For instance, in our shopping example, if you looked at the hours of 7 a.m. to 8 a.m. in March of 2021, this might not be reflective of all hours throughout the day due to COVID. Why? Well, we know that many stores reserve the morning hours for senior shopping. If we're considering a store where seniors are unrepresentative of the clientele, this may cause issues making our sample unrepresentative of the study population more broadly. Measurement error concerns not the sample as a group, but rather the individual measurements that are taken. If a measurement is not accurately taken of the quantity of interest, then this will cause further concerns with our estimate. For instance, if we asked people to self-report their heights, they may lie or misremember. If we were to measure their heights directly, it may be the case that we read the number off wrong, or we measure different quantities on each person. What if someone has tall hair, for instance, or if they're wearing heels? Both sample error and measurement error render our estimate, theta hat, to be a bad estimate for theta2, the study population's attribute. This means that even if we eliminate study error so that theta1 and theta2 correspond with each other, theta hat may still not be an acceptable estimate. What happens if we can confidently say that both sample error and measurement error are not a concern? Well, it's important to note that this does not mean that theta hat equals theta2. Even when there is no sample error and there is no measurement error, our specific sample is still subject to variability. The exact sample we get will dictate the value of theta hat, and in general, this is not going to be exactly equal to theta2. Instead, all we can conclude is that theta hat should be a good estimate for theta2. So, if we have no study error, we can conclude that theta1 is the same as theta2. If we have no sample error or measurement error, we can conclude that theta hat is an acceptable estimate for theta2. As a result, if there is no error at all, then our estimate theta hat should be acceptable to estimate the parameter of interest theta1. So this was certainly a lot of information, but I hope that it clarified some of these important concepts. Remember that all of these topics have been covered elsewhere, and if you need a deeper investigation of these ideas, you should turn to the specific instances where they were brought up, whether that's in the lecture content, the course notes, both Stat 230 and 231 course notes, or past tutorial videos. Of course, if you have any questions, please reach out to your instructors and we will do our best to answer them. A reminder that your midterm project is due next week, which gives you a little bit of a break from quizzes and assignments. This week, the course material continues to investigate hypothesis testing, which is a crucially important bit of statistics. I promise that in the next video, we'll dive deep into those topics and make sure that you are comfortable with all of them. Until then, I hope you all have a wonderful week, and thank you so much for watching.